Hello, everyone. Okay, so we're just going to do a little. I want to go over this review that you guys on Wednesday are missing, and I'm just going to go through it, pointing out the things that I said on Monday, but in a shorter form here without a great deal of extra talking. So, the first thing you need to know is for the final exam, I recommend studying your midterm 1 and midterm 2. The given midterms, in that you should be studying the material that is actually on those midterms, not the breadth of material that could have been included in those midterms, but what was actually asked in those midterms to help kind of focus your studying down into a more reasonable amount of material to study. And in terms of what comes after midterm 2, do the problems in this review. Make sure you understand how to do those. Make sure you can do the problems we did on Monday in lecture that I've posted as well in files on CI Learn under exams. And I think I called it like final exam lecture practice or something like that. And then, of course, anything that you feel rusty on, go back and look at homework problems like that. Look at examples like that from lecture. All right, so just to get through this review, the review starts with, we started with vector math. So I'm just pointing out to remind you the different vector math things we did all semester. Now that you've gone through the semester, you know how vital it is to understand this. If there's any bit of this that you're feeling rusty on, you want to go back and make sure you understand it. You need to be able to convert between Cartesian and polar and Cartesian. You're going to do that with Pythagorean theorem. You want to make sure you remember that the Cartesian angle is especially described so that we all agree that polar angle is coming off the positive x-axis in the counterclockwise direction. You get the length by using Pythagorean theorem. You do the angle by doing some inverse tangent if you know x and y, inverse sine or cosine if you have the hypotenuse. And remember, the dot product was described in this section as well. Then we talked about position. We talked about velocity. We talked about acceleration. We moved on to 2 dimensions and used our equations of motion in the x and y direction independently for something that's moving in 2 dimensions. In the case of projectile motion, we have constant velocity happening in the x direction, and we have constant acceleration happening in the y direction. That means in the x direction, you're going to use the constant velocity equation. There's only one option there. But in the y direction, you can use any of the 3 or more than one, any combination of the 3 constant acceleration equations in the y. Make sure you're rewriting it in the y direction because in your equation sheet it is in the x direction. Once you've done this, you will then solve your set of equations. You'll have a set of equations once you've filled in all your knowns here. There are always 3 options for projectile motion problems in terms of what the picture really looks like in real life. You've got some object that's being launched forward, and either purely forward, forward and upward, forward and downward, or in this case over here, purely forward. In all of these cases, you're going to have a different initial velocity vector, but the initial velocity vector is going to be the magnitude of the x and y components will be given to you by these equations. In this case, purely horizontal, the full launching velocity magnitude, the speed of the launch, is in the x direction. So v naught x is just v naught, and v naught y is 0. In this one, you get these equations exactly as they are, giving you the x and y components here. And in this one, you get the same thing as you do here, except the y direction, be sure to make it negative if it's going downward initially. If you're the phrasing you'll get in your word problem be something like was launched horizontally, was launched with some angle above the horizontal, was launched with some angle below the horizontal, in which case the theta here is the angle given. You have to know your x and y components because you need to write them in for your initial velocity in the x direction and that initial velocity in the y direction that you have in all of these problems. Next, we talked about forces. In terms of forces, we have, it's important that you're starting with your free body diagram. Down here, start with your free body diagram. Make sure you're including a reference frame with that free body diagram. Make sure you break any vectors that are not purely in an axis direction into the axis components, the Cartesian components, either an x direction and a y direction, or a radially inward direction and a y direction. Use one axis when you're designing your reference frame. You need to make sure one of your axes is in the direction of acceleration of the object, so that when you have an object that's going in moving horizontally, you're going to be using a standard XY frame. If you have an object that's moving vertically, you'd have a standard XY frame. If you have an object that's moving in a circle, you must have a, oh, I'm pointing to the wrong ones. You would have an XY frame, this way, XY frame. If you have something moving in a circle, you need to make sure you have a radially inward direction and then like a y direction to go with it. So one of these here, the y, once you've picked the axis that's in the acceleration direction, the other axis just needs to be perpendicular to it. So you got your radially inward direction and then perpendicular to it. You've got your horizontal direction and the perpendicular to it, or you have your vertical direction and perpendicular to it. If you have an inclined plane, you're going to tilt your axis so the x is along the surface of the plane and your y is perpendicular to the surface of the plane. But if you have a circular frame, a circular motion with your object, then you want to make sure that you're using the radially inward direction, regardless of whether or not it's on an inclined plane. There are, as you fill in your equations here for the force, there are many forces to make sure you're including if they exist, just regular pushes or pulls by people or animals or whatever. Gravity, when you use gravity, you always are choosing between either near the surface of the Earth or the universal law of gravity. So you have to decide which one's appropriate. If you're just doing a standard near the surface of the Earth problem that doesn't need extreme accuracy, you'd be using mg. If you're doing something out in space, an orbital problem, anything where you're asked about the forces between two masses, you're going to be using the universal law of gravity. If your object's touching a surface, make sure you include a normal force. Point it perpendicular and away from that surface. Friction, you've got kinetic and static to choose from. You would never have both in the same direction because it's either sliding or it's not sliding. It can't be sliding and not sliding in one direction at the same time. So remember, your static friction is less than or equal to your kinetic friction. You can always plug in the value in terms of its coefficient of kinetic friction and the normal force. But the static is going to be up to its maximum value. Often we end up plugging in the maximum value because we're looking for the point at which it is just about to slip. And you would be aware of that as you're reading through your problem. If you see just about to slip, what is the maximum velocity before it slips, or that kind of phrasing, you're going to be plugging in the maximum value for this. You want to point all of your frictions either in the direction opposing the slip or in the direction opposing the direction it would slip if it were to slip. If you have ropes or string, you want to make sure you include a tension. That tension would be along the rope or string and in the direction that is with respect to the object. So you're drawing the rope into the picture in your free body diagram. And always point it away from the objects because ropes can only pull. Energy. Next, we talked about energy. The initial energy is here, the total initial energy. As you fill that in, you have different energies to choose from. You can do kinetic if the object is moving at that point. You do gravitational potential, just the standard. If it's near the surface of Earth, you're using this one. If you're out in space, you're using the full universal law version. And then springs, if it's touching a spring that is compressed or stretched, then you have spring potential energy. You're going to use the same list of energies as you fill in the final energy. So this energy is at the initial point of interest. This is at the final point of interest. This is the work done that's through non-conservative forces between those points. That would be transferring energy into or out of the system. And you're going to calculate that this way. Either the force and the displacement have a consistent relationship, and so there's no change throughout the path that this force is acting. That angle doesn't change, and the magnitude of the force doesn't change. If that's the case, you'll just have this relationship. If you've got a function for the force as a function of position, or the angle is changing, you would need to have a function as well that you could then integrate. Anytime you're integrating, remember, you'd need a function. We don't just integrate things that aren't functions. So if you were given it as a function, that's a good clue that you're probably going to have to integrate. Next, we talked about momentum. The definition of momentum is mv. Conservation of momentum. Momentum is always conserved as long as there's no external forces acting, which means we can use this anytime we have a problem that has some sort of contact change between all the objects that are part of our situation. So if two people are on a sled and one person jumps off, that's a change in the way things are contacting each other, and you need to calculate the new velocity of everything when the person jumps off, and so you would use conservation of momentum to do that. Once you've done that, you may use energy considerations to talk about what happens after that contact change, but the initial point for the energy considerations would be just after the contact change. There is no conservation of energy like for standard contact changes unless you're told it's elastic through the contact change. So anytime things change the way they're touching each other, stop, break apart your problem there into two parts where you've got a before and after the contact change. You're using conservation of momentum to describe velocities before, and conservation of momentum, final momentum, will give you all those velocities afterwards. We also talked about impulse here. This is where a force over some period of time creates a change in momentum. And so if we integrate the force with respect to time, we can get the change in momentum. In this case, you often have a function here for your force, and it would be a function of time, and you'd be interested in the change in momentum, mv final minus mv initial. Torque. Torque we talked about right at the end of midterm 2's material. So it's R cross F. Remember, the cross product can always be written, if you're only interested in the magnitude, you can get the two vectors involved in the cross product, you multiply their magnitudes and sine of the angle between them. you need to use your right hand rule if you're using this version and you still need a direction. You would do your right hand rule for R cross F. In static equilibrium, you can solve those problems now that you know what torque is, using not only the sum of the forces is 0, but the sum over the torques is 0, which allows you to solve torque problems, static equilibrium problems, where you have two unknown forces in there. You can place your axis of rotation around on top of one of the forces you don't know in order to remove it from the equation, because the torque would be 0 if the force is acting at the axis of rotation. And so that removes that unknown force from your equations, allowing you to solve for the other one. This is something to always bear in mind when you're doing static equilibrium problems. Next, we talked about angular momentum. In terms of angular momentum, there are kind of two ways generally at this level to treat it. You've got a point mass that you're interested in the angular momentum about a specific point in space. And when you're using this equation, that point in space that the angular momentum is being measured around is the origin. So the position comes off the origin. Your position vector R is coming from the origin. The momentum that your object has, which would be a particle, be treating whatever it is as a particle, R cross P is going to give you the angular momentum of that mass M about the origin. So just place your origin wherever you're interested in measuring your angular momentum about. The alternative here is you can use the angular momentum, the portion of the angular momentum in the direction of the angular velocity, omega, is equal to I omega. Generally, this is for our equation, our questions that we're doing in this class. This is actually the full angular momentum as well. Sometimes for more complex problems, the angular momentum isn't actually fully in the direction of omega, and so you're just getting a component that's projected onto omega. In this case, we want to make sure we're using I, the moment of inertia. For I, you can either use the moment of inertia for a point particle, and that would be mr squared, where r is the distance away from the axis of rotation, and m is the mass of the point particle. And you can treat anything as a point particle if it's an appropriate choice, and that would be fine as long as you're interested in this object about an external axis, and it's not like spinning around its own center. Just remember, you can treat extended objects as point particles as long as the momentum you're interested in is the momentum about the axis you're choosing your r to be, and you're not interested in the angular momentum about something else. You can integrate r squared dm in this case if you need the full extended mass. You aren't just treating it like a point particle. That's a much more complicated moment of inertia because you have to do that integral. Or somebody else could have done the integral for you and you get it from a table. The table is really just this having been done for you. You have conservation of angular momentum available to you as long as there are no external torques acting on your system. So it's just like the linear momentum. And we had some pretty simple problems like this about, if you go back to the lecture notes, an ice skater spinning, and you had some homework problems with this one as well. You would have an I1 omega 1 equals I2 omega 2. You have to know the change in the moment of inertia to get the change in angular velocity. Generally for these problems, there wouldn't be anything we didn't get into great difficulty in these problems. We kind of had to move quickly through this section in the textbook, so in terms of the final exam, you wouldn't be getting anything heinous with angular momentum. It would be more just making sure you know how to use these equations and calculate everything. Next, we talked about gravity, the universal law of gravity, a more accurate version of gravity when we're not near the surface of Earth. Then we can use this. Or if we need really higher significant figures, we should use this even if we were near the surface of Earth. And then the way to use this is to remember that this is the force between 1 and 2, mass 1 and mass 2. When it's written this way, you want to think of it as the force on 1 due to 2. The force is pointing in the same direction as R12, which is the vector from 1 to 2. And that tells you which force this one is. This is the force on 1 due to 2, not the force on 2 due to 1. Otherwise, it'd be pointing the other way. You want to make sure you get your vectors right when you're writing them down for these types of problems. So make sure you draw your picture. Make sure your R is pointing the correct direction. Your R that's going in here should match the direction the force would be going. Your R hat, R12 hat, the unit vector in the 1, 2 direction, you're going to calculate by using the full vector, R12, and then you just divide it by its length, so you get a vector in the direction R12, but with just a length of 1. Then we can multiply that vector by the magnitude of our gravitational force to get a vector in the direction 1, 2, but with the magnitude of the force we need. We use the magnitude of this force when we're doing orbit problems because our force in the radially inward direction is the gravitational force, the universal law of gravity force. So we plug that in here. And then when we've got an object going in a circle, the m is our the mass that the m2 is the mass that's going in the circle, that's moving in the circular motion, so that the right hand side mass is mass 2. The centripetal acceleration is often written as omega squared r for orbitals because often we're talking about the period of the orbit, so we'd be plugging in a 2 pi over the period for omega. The thing you do need to be a little careful with these problems is to make sure that you are going center to center for your R12. Your R12 needs to be center to center. So if you're given the distances in terms of the altitude, you would need the radius of 1, and then the altitude goes off the surface to object M2, and then your R12 would equal the radius of 1 plus the altitude. Alternatively, you could have been given the orbital radius. If you're given the orbital radius of M2, that is that is R12. The orbital radius is from center to center by definition. You could be given the information about the distances between these two things as like, okay, you've got a central object with a radius R1. You've got an orbiting object with a radius R2. And then you have the surface to surface distance between these two things, d. In that case, the R12 would be the radius of 1 plus the surface to surface distance plus the radius of 2. So you need to know what altitude means. Altitude means it's off the distance from the surface of the central object to the center of the orbiting object. The orbital radius is from the center of the central object to the center of the orbiting object. And and then if they're just using words like you're just describing it, you need to make sure you're calculating that R12 to be from center to center. Oscillators. Next, we talked about oscillators. You need to make sure you're treating your oscillators appropriately. You can deal with oscillators in terms of their energy. The total energy will be the energy at all times as long as we don't have any non-conservative forces, which we didn't cover this semester. So the energy total should remain constant in time. That means whatever total energy you have, it will equal 1/2 mv max squared when your oscillator is going through the equilibrium point and it has its maximum velocity. And that total energy is also equal to 1/2 mk. This is really a squared. The maximum displacement, delta x max, is your amplitude. For a pendulum, it would give you the Vmax. It would also, but instead of the amplitude, what you're getting is the Y max. Remember, your amplitude for a pendulum is the maximum angular displacement, not the maximum height. So you need to convert between the maximum height and the maximum angular displacement there. The equation of motion for this that we would be using is the position as a function of time, the amplitude cosine of the angular frequency omega times t plus the initial phase shift if there is any, and the velocity of your oscillator is just the derivative of that with time. So you have minus a omega sine of omega t plus that phase shift. If I plot the position as a function of time and I go from peak to peak, I'm getting the period, and the amplitude is the distance from that central line to the maximum or minimum point, that distance. So your amplitude is always positive number. Next, we talked about waves. Excuse me. Waves are a more complex function. Their displacement is described by a sine of kx plus or minus omega t plus some phase shift. Remember, the minus is if it's traveling in the positive x direction, and the plus is if it's traveling in the negative x direction. So you have the opposite sign there you have to keep track of. If I plot it in position, I would be getting my peak to peak distance as my wavelength. But if I plot the displacement with time, the peak to peak wave distance is my period. It doesn't have to be peak to peak. Like I've drawn it here, one full oscillation, whatever that happens to be. So in this case, I did the from 0 back to the same 0. Then we did standing waves, which we mostly talked about in terms of instruments, musical instruments. So we've got 3 different types, which really boil down to 2 different types. We've got 2 ends that are the same, open, open, or fixed, fixed. It would also be true for closed, closed, because closed, closed is just like fixed, fixed. We have one mathematical relationship to describe those options. So same ends has all mode values available to you. M equals 1, 2, 3, 4. And when you look on your equation sheet, it'll be the one that has all the m's available. 2L over m, where m is 1, 2, 3, dot, dot, dot. The other option is the closed open, where you have different end types. This would be also valid for the fixed free. And in this case, you only get odd values of m's. And make sure you know how to draw all of these. Make sure you know where the antinodes and the nodes are. You need to know that the mth harmonic, that is your m number. So if it's the 4th harmonic, m equals 4. If it's the 7th harmonic, m equals 7. M equals 1 is your fundamental. So if you're asked for the fundamental frequency, you're using m equals 1. The frequency of the mth harmonic is m times the fundamental frequency, and the wave speed is the wavelength of the mth mode times the frequency of the mth mode. Remember, your wave speed can always be calculated by lambda times the wavelength times the frequency. And so as long as you know the wave speed, you can go back and forth between lambda and f. Doppler shift, we just did this one, so I'm just going to skip through. We did it in lecture. In terms of these examples, I've given you an example for projectile motion. This one's slightly different because I did an initial launch that was below the horizontal, which is less common launch in problems, but it just makes your y value negative to begin with. Make sure you keep your constant velocity in the x direction, constant acceleration in the y direction, pick the right equation, solve your set of equations, convert your v naught into Cartesian, so you've got an x component and a y component initially that you can plug in here. The next one I gave you was an impulse problem. This person is pushing your go-kart, your friend is pushing your go-kart with a force as a function of time, and that function's given to you. That tells you that you're likely to be integrating if you have it in terms of it being a function. That force over a period of time will create a change in momentum. So in this case, you start from rest and go to a final velocity. So you know your change in momentum given your mass, and that force integrated over time will create that so that you can calculate the amount of time your friend pushed you. You just have your evaluation points. You're going from 0 to t, where t is the time that they pushed you. You solve for t. This one's a orbital problem. Make sure that you are using your uniform circular motion to start with. You've got your universal law of gravity here for your force. There's only the one force. On the right-hand side, you're plugging in centripetal acceleration. The satellite mass will cancel out. It only depends on that central object's mass. And then you plug in for omega pi 2 pi over the period because you want to solve for the period, so you need period in there. And then you just solve using this one had an altitude and a radius, so you want to make sure your r value that you're plugging in here, these are always the same r because center to center is always the same as the radius of the circle. And so this one's altitude plus the radius of Earth. It's that version of center to center. Our oscillator problem here, we're given a problem that we use both the energy conservation and the position as a function of time to solve. So make sure you're comfortable with both of those things. And don't forget you do have these relationships for the period for your oscillators. For the mass and spring oscillator, you have it. You also have it on your equation sheet for a pendulum oscillator. And the period is related to that frequency that you're plugging in there. This one's a Doppler shift problem. It's a Doppler shift in combination with an instrument and a standing wave on that instrument. This is a wind instrument. Your wind instrument, this one's open. I would tell you for a wind instrument what type of instrument it is so that you don't try and figure it out. But if it's a string instrument, you can always assume that's a fix, so I wouldn't be telling you. Make sure that you know how to use the Doppler shift, and remember that in the Doppler shift, the speed of the wave for all of these Doppler shifts that are sound that we would be doing, which is everything we're doing up to now, the speed of the wave in the with respect to the stationary media, the wave speed VW, is just the speed of sound in air, which is on your equation sheet, 343 meters per second. In this case, we are moving away from the person playing the instrument. So the source is stationary and the observer is moving. That's why we're using the V observer version. We're moving away, so the frequency should shift down from what the source is making. So it should be the negative in the numerator to make a smaller number. The frequency of the source is then higher than the observed frequency. The frequency of the source we calculate is 450. That is indeed higher than 430, which is good. This source frequency is the second harmonic of our instrument. So that's the F sub 2. We're going to be using M equals 2 here. We can use the standing wave equations, but remember those are in wavelength. And most of our instruments, we're talking about frequency because we're talking about sound, and the pitch is the frequency. So a lot of times we're working with these problems in terms of frequency, but the equation we use to describe which waves are standing waves is based off of wavelength. It's the 2L over M. So we want to make sure that we know how to convert between frequency and a wavelength for any wave that's a traveling wave. And you're going to do your wave speed for that. So always remember your wave speed converts between lambda and F. I'm going to use this relationship and plug in my F for my F2 and solve for L. I'm plugging in M equals 2 because it was a second harmonic. Solve for my L, and then I get the length of my instrument. All right, so you can email me if you have any questions, and don't hesitate to do that. I know we ended up having to cancel Wednesday due to air quality. So make sure you are studying your previous midterms. Make sure you know how to do all of those equations. All of those questions on those midterms. Make sure you download the newest version of the equation sheet and are practicing with it. Use these practice problems I gave here, plus the ones from lecture on Monday that are posted, plus your practice exam, all of those things together to study for your final. And then if there's anything from those that you feel you need more practice on, go back to in-class lecture examples first, then your homework examples of those. And if you want even more examples of those types, you can always email me and I can provide you with some more examples. All right. So, and that's it. This is much longer than I meant for it to be.